Okay, now let's look at the periodic table real quick. Now these elements are organized and displayed according to their atomic number and arranged in a series of rows and columns based on shared chemical and physical property. So this is a good description. Like we said earlier, it's based on number of protons, right? So you start with an element that has only one proton, which is hydrogen, and you go all the way to the heavier elements that have more protons, and then so you end at 118. And then when you look at each rows over here, they're gonna have the same number of shells. We'll talk about that. And then the elements in the same columns, they will have the same number of electrons in their valence shell. Okay, so what are those terms mean? Let's look at this picture. So we said earlier that electrons are flying high speed around the nucleus, right? But these electrons have different energy levels. Okay, so some of them have lower energy, some of them have higher energy. So we kind of simplify things a little bit. We assign different shells to or orbitals to these electrons. So let's use an orbital because you can imagine like a satellite flying kind of around the Earth. So we have 3 orbitals indicated in this picture. So electrons with a lower energy are going to fill the orbital that's closest to the nucleus first. Okay, so this one end is going to be lowest level. So the electrons in this orbit is going to have the lowest energy. And then as the energy level increases, you're going to have orbitals that are further away from the nucleus. So electrons in 2n will have a higher energy than electrons in 1n, and then electrons in 3n in this picture are going to have the highest energy. All right, so these are the shells, or you can call it orbitals. We have a rule called the Octet Rule. Now you know what octet means, the number 8. Okay, so when we look at the electron shells, the outermost shell is called the valence shell. Okay, so the definitions here. This is the valence shell. Now the octet rule states that, with the exception of the innermost shell, so the innermost shell will be over here, this one, it can only hold 2 electrons. Only 2 electrons. 1, 2. Now this is an exception. Usually, the valence shell, the outermost electron shell, can hold up to 8 electrons. Up to 8 electrons. And when it is 8 electrons, the atoms are more stable energetically. Also just chemically more stable. Alright? So let's go over this one more time. If an atom can have only one shell, this innermost shell. So for example, hydrogen, it only has a 1 electron, right? So this shell can only hold up to 2 electrons, up to 2. So for hydrogen, it will be 1 electron. And what's the next element? Helium. So helium has 2 electrons. All right. Now, with the exception of this, all the other shells can hold up to 8 electrons. And when it gets to 8, this atom is going to be chemically stable. Okay. All right, so let's do a quick practice. So based on the octet rule, can you draw the electron configuration of sodium? Now to make things a little bit easier, I already showed you the picture over here. So if you go to the periodic table, you have to use the periodic table, find the sodium. So where's sodium? Right here. Okay, so the atomic number is 11, so that means sodium has 11 protons and 11 electrons. So let's draw. So you're going to fill the innermost shell first because it's the lowest energy. So you go from lower energy to our higher energy. So the first shell can only hold 2. Okay, so you put 2 electrons there, and then how many do you have left? You have 9 electrons left. Now you're going to try to fill the next level. Now the next level can hold up to 8, right? So you have 9 left, so you can definitely put 8 in here. And then the next level, you only have 1 electron left, so you just have to give that level 1 electron. Now, do you think sodium is chemically stable, energetically stable, based on the octet rule? No. So you can see there's only 1 electron in the valence shell, right? So it's not 8, so it's not going to be stable. It will want to react with the other elements so that it can get to 8 in the valence shell. Okay, so the valence electrons are the electrons in the valence shell. We'll talk about that. Now, when its valence shell is full, meaning there are 8 electrons, an atom will be unreactive, or we call it inert. Okay? When an atom's valence shell is not full, it will want to react with other atoms in order to fill its valence shell to get to 8. Alright, so here are a couple of rules. Now, if the valence shell can hold a maximum of 8 electrons, right? And then when it gets to 8, it's stable. But right now, there are only 5 or 6 electrons in the valence shell. What do you predict the atom will try to do? So I have an option here. Do you think the atom with only 5 or 6 electrons in the valence shell will try to take or gain electrons, or donate or lose electrons by sharing or taking them from another atom in order to complete its valence shell? So I'll give you a few seconds. You make a choice. Okay, so the answer is going to be, it's going to try to gain. So I'm just going to make it easy. I'm just going to highlight. So it's going to try to gain electrons. And the reason is that it's so close to 8, right? So it's easier to just take, 1 or 2. Here I can add 7 as well. 7. So it's easier to just take a couple, right, from another atom or share with them to get to 8. Okay, that's a shorter route, right, to get to 8. So on the other hand, if the same valence shell only has 1 or 2 electrons, or maybe even 3, right, the atom will likely to do what to get to a complete valence shell? So again, I'll give you a few minutes or a few seconds. Okay, so the answer is donate or lose, right? Because it's easier to just lose 1 or 2, and then you get to the previous level, which has 8, right? So now the atom is stable. Okay. So this is the answer, donate or lose. All right, quick practice. Assuming all the following atoms are in a neutral state, which atom will likely be chemically inert? So we mentioned this term earlier. So inert means it's not reactive, and the reason is that you fulfill a complete valence shell, right? You have a 2 for the innermost shell, or you have 8 for the other shells. Okay, so I'll give you a few seconds and you to think about which one is the correct answer. Okay, so basically you're looking for number 8, right, in the valence shell. So let's see. Let's go from here. Lithium. So lithium, this is the valence shell. How many electrons do you see? 1. Now, is it 8? No. So what do you think lithium will try to do to be inert? Yeah, it's going to try to lose this electron, right? And then they get to 2 for the innermost shell, and then this atom is stable. Okay, let's look at fluorine. So let's count 1, 2, 3, 4, 5, 6, 7. Now 7 is it 8? No, it's so close, but it's not 8. So fluorine is not inert. Now what do you think fluorine will try to do to get to a stable state? Right, it's going to try to take away an electron from some other atoms, right? Now, if it takes electron, then it gets to 8. So it will be chemically inert. What about oxygen? Count 1, 2, 3, 4, 5, 6. So again, it's not 8. It's going to try to take 2 more electrons from another atom to be chemically inert or unreactive. So the correct answer is B. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. So argon gas is very, very stable. Okay, let's go chemical bond. So atoms form chemical bonds with other atoms nearby, and then they will obtain electrons they need to attain a stable electron configuration, and that's the octet rule, right? 8 for the valence shell. So when these atoms chemically bond with each other, the resultant chemical structure is a molecule. So for example, H2O, water, is a molecule because you have two hydrogen atoms and one oxygen atom chemically bond with each other. So that results in the water molecule. Now we're going to look at each type of chemical bond. So before we look at the first one, ionic bond, let's look at the definition for ions first. So we talk about some of the atoms, because they want to become stable, they may gain or lose electrons, right? And then when that happens, they form ions. So because electrons carry negative charge, and an atom loses electrons, it becomes a positive ion. Okay, when you lose electrons, you lose that negative charge, so now you're positive. Okay, and then we call positive ions cations. There you go. And if an atom gains electrons, now it becomes negative, right? Negative. So we call them anions. So negative ions are anions. All right. So the two terms are very similar. So I just have a trick for myself. If you're a cat lover, right? You like animals. Now cat ions. So you can say, oh, cats are good. So cat ions are positive ions, right? They're good, they're positive. And then the other one, the anions, are negative ions. Okay. So in order to form an ionic bond, we have to have electron transfer. So this usually happens between two atoms. One atom wants to lose an electron, and then the other one wants to gain an electron. So a good example is here, sodium chloride. That's our table salt. So sodium has one electron in the valence shell, so it wants to just lose it to get to a chemically stable state. And chlorine has a 7, so it really wants to gain 1 to get to 8. So when they meet, that's a perfect match. So sodium will transfer 1 electron to chlorine. So now sodium becomes positive sodium ion, and the chlorine becomes negative chlorine ion. Okay, and then the bond they're forming is called ionic bond. Okay, so ionic bonds form between ions with positive charges. Okay, so here's a quick question. I'll give you a few seconds. Okay, what is likely to happen to the electrons when the potassium atom bonds with a chlorine atom? Now, first of all, you have to figure out how many electrons are in the valence shell for potassium, right? You kind of know what's it like for chlorine from the last example, but now we need to figure out what's the configuration for potassium. All right, so just to make things a little bit easier, let's go back to the periodic table. So potassium is right here. It has 19 protons, which means it has 19 electrons. So let's come back here. So how do you assign the electrons if you have 19? Now we talk about the innermost has to have 2, right? So okay, so this is for potassium. So you get 2, and then the next level will be 8. And then, so now it's 10 electrons, so you have 9 left. So can you fulfill the next level with 8 electrons? Definitely 8. So now you have 1 electron left, 1 electron. So you can see potassium atom has a 1 electron in the valence shell, so it wants to lose that electron. And it's perfect because chlorine atom just needs 1 electron to be chemically stable. So potassium is going to transfer 1 electron to chlorine. So the correct answer is C. Potassium loses 1 electron and chlorine gains an electron. Now the answer is not going to be B because they don't really share electrons. The chlorine is like a bully. All right, the chlorine atom would just take the electron away from potassium. They don't really share anything. Okay, so it's a complete electron transfer. So this is ionic bond. Alright, we're going to continue on chemical bonds. We talked about ionic bond last time. Now we're going to talk about the second type of chemical bond, covalent bond. The atoms can either just completely lose or gain electrons, that's the ionic bond, or they can be a lot nicer to each other. They can share their electrons. So when they share the electrons, that will result in a covalent bond, right? Co means kind of work together, so you share the electrons. So usually these covalent bonds are pretty strong, and then they're much more common than ionic bonds in the biomolecules of living organisms. Okay, so in the next chapter we'll talk about all those biomolecules, and you can see the covalent bond is really prevalent in those molecules. So here's a quick example of covalent bond. So now we're looking at oxygen gas. You know, oxygen gas consists of 2 oxygen atoms, right? And then if you remember, oxygen atom has 6 electrons in the valence shell. So when you have 2 oxygen atoms together, they have the same capability of taking electrons, right? They want to take 2 electrons, but nobody, right? Neither atom can really lose electrons because they have the same strength. So they're going to compromise a little bit. They decide to just share the electrons. So it's shown here. So they both will offer 2 electrons to share. So now when you count the electrons of valence shell, 1, 2, 3, 4, 5, 6, and 7, 8, right? So now it fulfills the complete valence shell. And this is the same thing for this oxygen atom. So you have 8, right? Including these 2 shared by the other 2 oxygen atoms. So this is the covalent bond. Atoms are shared instead of just being taken away. When you look at covalent bonds, there are 2 types. The first one is called polar, second one is nonpolar. So polar covalent bonds will result in unequal sharing of the electrons. So the end result is one atom will be slightly positive or negative. Okay, so in this case, this is hydrochloride. This is a very strong acid. So chlorine has 7 valence electrons, and then hydrogen only has 1. So what happens is hydrogen can't really lose that electron because it only has 1. So it's going to share the electron with chlorine. But chlorine is a lot more stronger than hydrogen, right? It has 7 electrons, so it's very powerful in taking away not completely taking away, but kind of making the electron closer to itself than hydrogen. So since the electron is closer to the chlorine, it's slightly more negative, and then hydrogen a lot weaker in sharing the electrons, so it's slightly positive. So when you have two ends that have different one is a positive, one is negative, then it creates a polar covalent bond. Okay, so a very sorry, a very important characteristic is that polar chemicals, polar covalent bonds will result in a very good water solubility. Okay, so hydrochloric acid, this compound can dissolve in water very easily, and that's because it's polarity. It's polar, right? Now, for nonpolar covalent bonds, the electrons are shared equally, so there's no slightly positive or negative end. Okay, so everything is equal. Nonpolar compounds do not really like water, so they don't dissolve in water very easily. Okay? I'm going to add a couple terms here. So usually polar compounds, they are hydrophilic. So hydro means water, philic means like, right? So they like water, so they're water soluble. In nonpolar compounds, they're hydrophobic. There we go. So phobic means dislike, right? Fear. So they don't like water. So they are not very soluble in water. So they usually do not dissolve easily in water. Okay. All right. So remember these terms: hydrophilic and hydrophobic. Okay, so here's the question. So I'll give you a few seconds. So the correct answer is this nitrate ion. Okay, so I have a picture over here, so you can see that oxygen has 6 electrons and the nitrogen has how many? 5. So neither of them can really completely take electrons away from the other atom, so they decide to just share the electrons. So they will form a covalent bond. Now they are not equal in their sharing ability, so this covalent bond will be a polar bond. For the other three, A, B, and D, you can see you have a sodium, you have a lithium. Remember, lithium and sodium are in this same column, right? And they only have one ion. Sorry, not one ion. One electron in their valence shell, so they will completely lose that single electron. So they are going to form ionic bond with the other atom. So the correct answer is C. All right, the last chemical bond that we're going to talk about is hydrogen bond. We talk about hydrogen bond is because it's very important, especially when we talk about DNA. So the hydrogen bond is formed by hydrogen, which is usually slightly positive, with another atom that's slightly negative. So the hydrogen electron in the polar covalent bond is pulled more strongly toward the other element. So in this case, it's the oxygen, and away from hydrogen. So this results in the opposite charges, right, for the oxygen and the hydrogen. So it's attracted to the neighboring negative charges, forming a weak bond called hydrogen bond. All right, so this may be a little bit confusing. The bond between hydrogen and oxygen, so this is a water molecule. The bond in between the hydrogen and oxygen within this water molecule is covalent bond, right? The hydrogen and oxygen share electrons, but they're not shared equally. So this results in the negative end on the oxygen end and the positive on the hydrogen end. Now, the hydrogen bond is between two water molecules. Now, of course, you can have more, but in this case, we have two water molecules. So, because this end, hydrogen end, is negative, is slightly positive, so it's attracted to the oxygen end of another water molecule. Okay, so they form a weak bond, and this is the hydrogen bond. Okay, so again, hydrogen atom with a slightly positive charge is attracted to a slightly negative part of another water molecule, and in this case is oxygen. So this is a hydrogen bond. Now, because it's formed in between molecules and you don't really have any complete transfer of electrons or sharing of electrons, this bond is pretty weak. Now, there's an advantage for being a weak bond. So when you look at the DNA molecule, most of you probably know that DNA has two strands, right? Two strands you can see here. They form a double helix structure. So there are chemical bonds in between the two strands to kind of hold them together. So this is, to maintain the integrity of a DNA molecule. So the bond that keeps the two strands together is a hydrogen bond. So you can see these dotted lines, those indicate hydrogen bond. And also the kind of orange part, those are hydrogen bonds. But you can't have a very strong bond because when you replicate the DNA, or when you need to transcribe DNA, you need to separate the two DNA strands. So you want something that's strong enough to hold the two strands together, but also weak enough that can be easily, broken so that you can separate the two DNA strands for replication or transcription. So hydrogen bond is a very good candidate. And this is the bond, in between the two DNA strands. Okay, so